In our last module, we looked at how we can use truth tables to determine the kind of logical statement that we have. Now we want to look in this module at how we can use truth tables to determine whether or not statements have particular important kinds of logical relationships to one another. And the first logical relationship we want to look at is that of logical equivalence. So here we have Kurt Gödel and Albert Einstein to tell us that two statements are logically equivalent to each other if and only if they have the same truth value under every possible circumstance. So they always have the same truth value. To determine whether or not statements are logically equivalent to each other, we're just going to make a truth table, put both statements on our truth table, the same truth table, fill out that truth table for both statements, then compare the truth values under that main connective, the last connective. Compare the truth values for those statements on every row. If they're the same, always the same truth value, then they are logically equivalent. If they differ even by one row they're not the same, then they are not logically equivalent. So let's look at an example of logically equivalent statements. So here we've got these two different logical statements. We put them on our truth table. I use a line to divide them up. And we fill in our guide columns. We transfer the guide columns onto the body of the truth table. Then we fill in our truth table for each of those formulas. So let's start on the formula over here. We'll do our tilde first, then our dot. Then finally we'll go outside those brackets and do our tilde. And that gives us the truth value under that tilde for this formula. Now we go over here. It's just got this one logical connective. We fill in the truth value for that using our rule for the horseshoe. Only way to make a conditional statement false is if the antecedent is true and the consequent is false. Now we've got that. So now we compare the truth values for these two different formulas under their main connective. That is the truth value for every row, every different way the world can be. And we see that they are exactly the same. They always have the same truth value no matter how the world turns out, and hence they are logically equivalent statements. If they differed on even one row, if say this was true and this was false, then they would not be logically equivalent to each other. Let's look at the next relationship. The next relationship is contradictory statements. Contradictory statements are statements that always have the opposite truth values. So to test for contradictory statements, you again fill out the truth table for both statements. You look under that main connective, the last one that you do, the one that tells you the truth value for that formula, every different way the world could be. And then if they always have the opposite truth value, every single row, they are contradictory statements. So let's look at some examples. Here we have these two formulas. We fill our guide columns into the body of the truth table. We start with our connectives and brackets. Then we go to that last connective. Here's the last connective for this formula. Here's the truth value for it. Here's the last connective for this formula. It's the truth value for this. True, false, false, true, false, true, false, true. They always have opposite truth values, so these two statements are contradictory statements. Let's look at a different set of statements, these two. Again, we fill in our guide columns in the body of the truth table. Let's start with our dot, then our wedge. We look at them. Same truth value. So these are not contradictory statements. Finally, we want to look at consistency and inconsistency. Two statements are consistent when it's possible for them to be true at the same time. There's at least one row where they're both true. If there isn't one row where they're both true, if they always have a difference, that is, they're never both true, then they're inconsistent. To test for inconsistency and consistency, we fill out our truth table for those two statements. We look under those main connectives and we see if there's a row. Just a single row is all you need. You can have more, but you need one where they are both true at the same time. If they're both true at the same time on a row, they're consistent. If there is no row where they're both true at the same time, they are inconsistent. So let's take a look at an example. Here we have P horseshoe Q and P triple bar Q. Fill in our guide columns in the body of the truth table. Here's our horseshoe. There's our triple bar. We compare them, and here's a row where they're both true. That means they are consistent. What about this one? Here we have two different formulas. Again, we fill in our truth values from the guide columns in the body of the truth table. Our horseshoe, straightforward. Our other formula, we'll start with our tilde. Then we'll go to our dot. We look under our dot, the main connective. Here's the truth value for this formula, every different way the world could be. Truth value for this formula, every way the world could be. There is no row here where they're both true, and as a result, they are inconsistent statements. So these are consistent. There's at least one row where they're true. These are inconsistent. There is no single row, no way the world could be where they're true at the same time. In our next module, our last module, we'll use truth tables to evaluate validity and invalidity of arguments.